In a landscape where 95% of the territory is barren,
Shifting sand and summer temperatures routinely shatter the 50 degrees Celsius mark. The survival of a modern nation is not guaranteed by nature, it is manufactured. Saudi Arabia supports 37 million people, yet the country does not possess a single permanent natural river or lake. For decades, the kingdom's urban centers relied on the slow, silent extraction of ancient fossil water trapped deep within underground aquifers. But this was a finite resource, a geological savings account with no possibility of replenishment. As the demand for water skyrocketed alongside rapid industrialization, engineers faced a stark reality: continue the current rate of extraction and invite a total socioeconomic collapse or attempt to bend the laws of desert geography to their will. The solution required a shift from internal consumption to industrial-scale generation. The ocean became the kingdom's primary lifeline, but desalination brought its own set of critical engineering challenges. Pulling billions of liters of seawater from the Red Sea and the Persian Gulf is an industrial process of immense complexity, far removed from simple filtration. To convert hyper-saline seawater into life-sustaining water, massive coastal plants utilize a multi-stage reverse osmosis process. High-capacity offshore intake pipes, spanning hundreds of meters into the sea, draw in raw water through screens designed to filter out marine life and large debris. But raw seawater is loaded with organic matter and microscopic pollutants that threaten to foul and destroy the delicate semi-permeable membranes essential to the desalination process. Engineers developed a rigorous pre-treatment sequence to safeguard these systems. First, seawater passes through gravitational sand filtration tanks, where a continuous flow of sand binds suspended particles.
this is bolstered by the precise injection of sodium hypochlorite for disinfection and iron 3 chloride as a coagulant,
which forces fine particles to clump together into sediment that can be easily removed. The water then flows through secondary cartridge filters, which act as a final barrier, catching impurities down to a size of 1 to 5 micrometers. Only after this mechanical and chemical refinement is the water ready for the core process. High-performance centrifugal pumps generate an immense 60 bar of pressure, forcing the water through reverse osmosis membranes. This pressure is so extreme that it isolates individual water molecules from salt ions on a molecular scale. The result is water of exceptional purity, but the process introduces a new problem. This newly created water is chemically unstable and dangerously aggressive toward the metal infrastructure of any municipal supply network. Without further intervention, this ultra-pure water would immediately begin leaching minerals from the steel pipes, leading to structural failure and potential health risks for the population. Engineers therefore implemented a sophisticated post-treatment phase. The water is stabilized through precise pH adjustment, followed by a controlled remineralization process, where calcium and magnesium are re-added. This not only makes the water safe for consumption, but also prevents the corrosion of the very network intended to carry it. Yet, even with this high-tech production at the coast, the logistical nightmare was only beginning. The kingdom's urban heart, including the massive city of Riyadh, lies hundreds of miles inland. How do you transport millions of tons of processed water across boiling desert terrain without losing the supply to evaporation or thermal degradation? Traditional surface-level canals or shallow exposed pipelines were dismissed as inefficient and vulnerable. In the extreme heat of the Saudi summer, surface evaporation would claim a massive percentage of the water before it ever reached its destination. The solution was the creation of a massive hidden infrastructure project, an 8,700-mile underground pipeline system often referred to as the Invisible River. This network is not just a pipe, it is a structural marvel designed to withstand the crushing pressures of the desert floor and the intense thermal cycles of the environment. The pipeline segments consist of high-strength carbon steel, each built with 25-millimeter wall thicknesses to resist both the massive internal pump pressures and the external weight of the surrounding earth. To ensure the integrity of the network, automated construction crews utilize hydraulic internal alignment clamps that feature 360-degree gripping jaws. This level of precision is vital, as every single weld is subject to automated ultrasonic testing to identify microscopic defects before a final multi-layer liquid epoxy coating is applied to combat long-term corrosion. The terrain itself fought back. To drive these arteries through the rugged Hijaz Mountains, engineers deployed tunnel boring machines and utilized controlled explosives to cut through solid granite and limestone. At peak efficiency, these specialized teams managed to complete 1.5 kilometers of pipeline installation every single day. By burying this system deep beneath the surface, engineers effectively decoupled the water's temperature from the 50-degree surface heat, preventing evaporation and ensuring the water remained pristine. This massive investment in subterranean transit acts as the structural spine for the country's future, but it serves a dual purpose. It provides the water security required for the Saudi Green Initiative, a landmark ecological project that aims to plant 10 billion trees across the kingdom. This effort is not merely an aesthetic choice, it is a deliberate engineering intervention designed to alter the local microclimate. Calculations indicate that this scale of reforestation can reduce atmospheric PM 2.5 dust pollution by as much as 20%, while lowering urban heat island temperatures by over 2 degrees Celsius. However, the scale of this success invites a final set of questions. The environmental cost of desalination is high, particularly regarding the management of brine, the concentrated, super-saline byproduct of the reverse osmosis process. Returning this brine to the ocean without disrupting marine ecosystems requires precise dispersal technology and sophisticated monitoring. Simultaneously, the energy demands of high-pressure pumps are immense, driving the industry toward an aggressive transition to integrated renewable energy sources to power the entire desalination fleet. Despite these challenges, the transformation is undeniable. Saudi Arabia has successfully navigated the limits of a hyper-arid climate by treating engineering as its primary resource. By merging the chemical mastery of reverse osmosis with the brute force logistics of a transcontinental subterranean pipeline, the kingdom has essentially created a synthetic hydrology. It is a system built not upon the presence of natural water, but on the ability to produce and secure it against the most hostile environmental conditions on Earth. The project serves as a global benchmark for how modern infrastructure can function as a buffer against extreme climate constraints. As the kingdom continues to refine its efficiency and expand its recycling capabilities, it transitions from a nation that survived in spite of its geography to one that manages its survival through technical dominance. The pipeline is no longer just a conduit, it is the fundamental proof that in the face of absolute scarcity, ingenuity remains the most valuable resource.
If you enjoyed this video, subscribe for more engineering megaprojects and technological marvels. And let us know in the comments, considering the extreme energy requirements of large-scale desalination, do you think advanced nuclear or solar thermal power is the better path for achieving truly sustainable water production?